Let's get started. I want to start the next part of the course today on derivative pricing. But before that, a couple of comments on the coursework, and if you have any quick questions, we can deal with this. When you're doing part 3 of the coursework, where we are trying to track an index, our job is there is the index that's going that way, and we have a number of components of this index. I said take about 30 of them, and the job is to find a subset of these which would best track that, by 2 different methods. The greedy method, whereby you pick the one that matches it best, hold it, then pick the second best that you can add. So you have a 2 in 2 asset basket that tracks it best. Then hold the second one, search through the remainder for the third one, which is the greedy one, that you will be implementing. The other one you will do is L1 regularizer, which is the lasso method, for which we took it from Brody's paper. There's a slight issue with this. The CBX solution to this doesn't work as well as I thought it would, okay, with the constraints. So if we try to minimize the index minus R times W 2 squared plus the norm of W with 1 with some weighting, with some weighting times the norm of W. This, in this form, the lasso solving the lasso problem as solved by CBX will work beautifully. It will pick you a subset, zeroing many of the coefficients. And by changing this tau, you can plot, say, a graph of as you increase tau, how does the number of selected components decreases. Some of you have done this for the machine learning coursework. Yeah? So this works well. If on top of this we add constraints like W transpose mu should be greater than some return, there's conflict between this constraint and this constraint at times, and it often fails. Okay? But for the purpose of selecting a certain set of a subset to track that, at that level we don't need these constraints. Okay? So when you solve the part 3, just do the unconstrained one in this way. Don't include the constraints. If you were to include the constraints, we could always hack this by selecting at some level a number of stops, and then with those adding the constraint. As another suboptimal solution. So if you crash with this one and you implement this in CBX, the answer is ignore the constraints. Just solve the sparsity using lasso regularizer, select a subset, compare it with your greedy solution, and you're done. Okay, is that kind of clear? Have you not reached this place, or have you reached this, got stuck, or does this not make sense? Or should I be saying this 6 hours before the deadline? Yeah. Right. Okay, so specific weird result we can look at on Monday. But you have to bring out of whatever you do 2 basic things. One is that the combinatorial search is impossible. Therefore, we do a suboptimal greedy search. The sparsity using lasso regularizer is a relaxed version of it. It's an approximate way of doing exactly the same thing, but with a very cheap way of doing it. Okay? They will never give globally optimal solutions on the training data. That's the first point. The second point is that you should not judge anything on the training data itself, or on the training data alone. You would use the training data to select a subset that best approximates this, and then ask the question, how would this work? How would this have performed? And the answer to that question is to say, if I had invested in this one, then over the next year or so, what might I have gained? You could formulate that, say, in terms of the Sharpe ratio. You could say, if I had invested this way, I would have gained so much with a certain variance. So you can divide by that and quote a sharp ratio. That is how one would do this in practice. Okay? Yeah.
How do we match in the greedy version, in the greedy algorithm? I mean, Euclidean distance or the one that approximates the most?
So that's Euclidean distance. Yeah. So that's the only thing you can evaluate on the training data. And the more and more things you add to this, or add the more and more you go greedy, this error will monotonically go down. Yeah. If you evaluate this error for the best W, minimize this error with 3 functions, and then compare it with 4 functions, it will go down. Yeah. But you can be smarter, and you can say, I don't want to run my greedy algorithm to select stocks based on that training set alone. I would just evaluate what it might have done on the next week out of sample. So that would be very similar to cross-validation you would do in pattern recognition. Yeah. You do not just base any conclusion based on training and testing on the same training data. You would retain part of your data as a validation set, train on this training set, and make a statement about how well it does on the validation set. Okay? Then whatever you see in things like neural net training, you will also see here. So as you increase the number of functions, the error that you make between this weighted combination and the index on the training set should monotonically go down. Yeah? If you evaluate it with some out-of-sample performance, you would normally expect it to go down a bit and then either saturate or even go up. Yeah? So you do the approximation within the greedy loop, but as you keep adding, you evaluate what happens to the sharp ratio on the subsequent week or something like that, then you would expect to see this. Okay? Is that generally clear to everyone? Yeah.
Are you expecting the same subset of stocks for both techniques?
No. Oh, I shouldn't say this. It's unlikely. It's unlikely. So the greedy search will try to match the ones that, as you would expect overlap, but both are different ways of selecting a subset. Yeah. So where you would see differences if there are stocks that are very strongly correlated. If they're very strongly correlated, after picking one of them, there is no incentive for the greedy algorithm to pick the next one, even though it is a very relevant one. Yeah, so you will notice that kind of thing. But then again, you're working with real data. Sometimes you might see it, sometimes you might not see it, depending on which stocks you have, which time window you have. Okay, but that's real life. Okay, any other quick question? Yeah.
So, with the constraint on it, it's just failing because there's no feasible solution? Is that?
It could be, yeah.
It's not probably.
Yeah, so I think Brody and them were very smart in their paper by specifically looking for algorithms that would solve with the constraints. Yeah, I tried to find a shortcut and that didn't work. But that's the answer. Okay, shall I move on to the next one? Yes, no, yeah. Okay, so the next one is the major topic on derivatives pricing. I sent you an email earlier with copies of the slides stuck somewhere. But there will be some errors that I need to correct. So from Monday it will be more valid than what it is now. What did I want to say? Yeah. So it's quite a interesting topic with lots of algebra. So what I want to do is to experiment with a different way of doing this. I'll take 2 passes through the topic of today. One today and one on Monday. And what I'll do today is to skip as much as possible past the algebra and then try and see what the insights are. What are people achieving to do, trying to do in this? And then on Monday we'll go through the same thing, but we'll spend a little bit more time with the algebra to see if those steps make sense. Okay. But usually if you had the algebra and if you had lots of time, table lamp, late night, you will get it, right? Rather than mixing. Okay, so what are these things? So we talk a lot about, one way of investing is to buy a stock and hold it, then sell it and make more money and so on. There are many instruments in the market that are based, whose value is based on the price of something else. Yeah, so those are called derivatives. So So you can say, I sell you a part of Southampton University, you own it, and then Southampton makes money, you get a dividend, you make money, and so on. You can also sell contracts that say that I will pay you so much money if Southampton University's value exceeds a certain threshold. Yeah. Or I can say to you, let's make a deal whereby in 6 months' time, I will sell you a share of Southampton University at a particular price. Okay, and we enter into a contract. And if we enter into a contract in 6 months' time, I am obliged to execute that contract. You come to me with this paper, I have to sell you Southampton University share at a particular price. So that sort of pricing problem is what we'll look at. Okay. In doing that, there's quite a lot of literature on fair prices, no arbitrage, efficiency of markets, and so on. What we are going to look at environments where we'll throw in arguments like, if I have a portfolio today which has a certain particular value, and with the strength of it, I issue you a contract of a future promise, yeah, that has to be a fair price. And what that fair price means, that if we don't agree on this fair price, there will be an arbitrage opportunity for somebody else to make money. Okay? So what is the equilibrium we will hit where there is no arbitrage opportunity would sit as an argument in the way we derive fair prices. Okay, so we'll hit this repeatedly, and here's an example. So there is a stock, Southampton University's share price is S0 today, say. Okay. Me and somebody else enter into a contract in which we say I'm going to sell, and that guy is going to buy Southampton University share at that price at time T, 6 months from now. Okay? And the kind of argument we will develop is that today, in order to have this stock that I'm going to sell this guy in 6 months' time, I would have borrowed that value from the bank, buy a share of Southampton, and keep it in my pocket and wait till 6 months' time. Yeah. And when this 6 months hits, I will sell this at price F according to the contract that we have made. Yeah. And I have to pay back the bank. And the amount I have to pay back the bank, assuming compounding interest at some risk-free rate that the bank is going to charge me, is of this value, e to the power t. Sorry, it's not e to the rt. Okay? So the no arbitrage argument says that the fair price at which we would sign this future contract, yeah, is this one, is how much I will have to pay back the bank in order to enter into this contract. Yeah, does it kind of make sense? Yeah, this is the best I can do. I start today, I have no net value because I borrowed and bought. Yeah. So what I owe the bank is the value of what I have, and that balance has to be kept in time T as well. And at time T, what I owe the bank is higher, so I have to charge the guy higher for F so that I can pay the bank back. Okay, we'll see such arguments later on as well. What are options in this? So options are contracts written on the price of an asset. An options contract will have two things in it. One is a strike price, and one is a time of maturity. Okay. So I'm going to make a statement like, I will sell you one share of Southampton. Well, I'm going to give you a piece of contract. Having that contract, you can buy from me a Southampton share at value K in 6 months' time. Yeah. So I have written this contract with you, I have signed it, and you're holding this. Okay. So we wait 6 months. Southampton has done extremely well, yeah, and the Southampton's true share price is very, very high, but you have this contract to buy it at K. Yeah, you will come to me, you say, okay, here's the contract, you're going to sell me at K. So I'll sell you at K, you will buy it from me, sell it immediately, and make money. Yeah. But has Southampton done very badly? Students have given very bad, I don't know, survey results, and stock prices of Southampton has gone down, the Vice Chancellor has resigned, whatever. What would happen? Southampton's stock price would be less than what's written on the paper, and your paper is worthless. There's no point in your coming to me and buying it at K when Southampton's share price is below K. Okay? So you can draw a payoff function for this. That is, depending on the value of the stock price, what is the reward that you get? What's the payoff from owning this contract It'll be 0 as long as S of t is less than k, then the strike price, it will grow linearly based on S of t after that. Okay? If this picture is clear, then immediately this one becomes clear. I can think of a contract called a put contract. A put option is one that gives you the right to sell at a particular price at a particular time t. Yeah? So the payoff has to be like this. If this asset price has gone above k, then your right to sell at k is worthless. Yeah? If the asset price is actually less than k, then you have a right to sell at k, whereas the true price is lower, so you would buy and sell, and you will make money. Okay, so the payoff will imply this. So these are the very basic ones. We'll look a lot at pricing these. So the question then, the pricing problem then is how much are you willing to pay to have this contract? Yeah, and that obviously depends on the uncertainty between now and what would happen at time t. Okay. The nice ways in which these things vary would be that, okay, so exercise is one of them. So the European style options contracts, you're only allowed to exercise them at that time of maturity. The contract is written for 6 months maturity, then it's only on that particular day you can come with this paper and demand something. Okay? American style contract enables you to exercise at any time between now and the writing of the contract. Okay? So what we will do is we will look at 2 or 3 different ways of pricing these contracts. Okay? One is we will, very similar to that what's done in most computational modeling things, we will make very simplistic assumptions about how things might change between now and time t. When I say very simplistic assumptions, those simplistic assumptions are sensible, not completely false, but very approximates of reality. Okay? But we would make those simplistic assumptions where we can handle the maths and derive closed form expressions. Okay? Reality is complex. Reality changes in all sorts of ways. If we can make decent approximations to reality, bring the world into a simple world, we can write the mathematics of this in a form you can solve it in closed form. And if you can do that, you can say something about the state of the world. But then at that point you realize that, of course, it is not true. It's what you wrote is only an approximation. And then you will ask the question, how might it have changed? Okay? And then make adjustments to your model to handle that scenario. So what we'll do is we'll make very simplistic assumptions, derive closed form, a particular closed form way of pricing options. And then, so that's very easily done for European style exercise options. You can see that's easier, that should be easier than this because it's restrictive, you can only exercise at time t. Yeah? So we make closed form expressions for this one. And then we ask the question, how can I solve this numerically? Can I think of a numerical model to solve this? And that numerical model will produce the same answer as the analytical model. Yeah, so they will be kind of happy that the numerical model is a good one. And then with the numerical model, we can ask other questions, like if I relax this assumption of exercise, can I solve that problem? Yeah, a problem that I cannot solve with simple analytical way. I would solve the simpler problem, derive a method, satisfy myself is a good method, and then build on that model to solve a harder problem. Okay? So that's the kind of pattern we are going to take. And in that, so once you have these 2 pictures in mind, there's a thing called put-call parity. There's a very nice relationship between prices of call options and prices of put options. Okay? And that's what this parity is called. So we derive this, and here also we'll see this no arbitrage argument. So we'll derive this by saying, okay, suppose I have a portfolio, call it P1, and what I have is a call option. I have bought from someone a call option, and I have some cash. And the cash I have is the strike price of that option times e to the power minus r of the time I have to the maturity of that option. Okay? You can already guess that what I'm calculating here is the present value of that k should I hit that strike price. Okay? So I just construct this portfolio. Let's see how it behaves. I'll construct a second one, which is a portfolio consisting of an European put option. Yeah, so I buy myself a put option, and I buy myself one share of this underlying stock that's sitting there. So of the symbols here, on this stock is written these contracts. The call contract and put contract both have a strike price of K, and both have time to maturity identical in T, and R is the risk-free interest rate. Okay? So how are these two related? So you can understand how they relate by looking at their values at time T. So at time T equals naught, initially, my portfolio P1 is worth the price of the call option plus the amount of money that I have. Okay? So I've constructed this portfolio to buy this call and have that much money, so that's the value of it. My put option has the value of the put contract, however much I paid for it, and I have one share of the underlying stock, so that's S naught. Okay? Let's see what happens to these two portfolios at the time of maturity. At the time of maturity, the values of the portfolio is obviously going to depend on what S is going to be, right? What S of T is going to be. And there will be two cases, if it's bigger than the strike price or lower than the strike price. So we go to time T. Suppose the stock is of price higher than the strike price, then the value of the first portfolio is I will gain this much by executing the contract, and I will have K money in the bank because I started with K to the minus RT, and that would have compounding interest would make it K. Yeah. So at time T, if the stock market is doing really well with respect to this stock, the value of my portfolio is the just value of the stock. Okay. What's the value of the second one? If the stock price is bigger than the strike price, your put option is worthless. Yeah. And you hold one underlying stock, that's ST, so that's ST. Yeah. So the way I have constructed this portfolio, if the value of the stock price is higher than the strike price, both portfolios have the same value. Yeah. Similarly, if this one is smaller than the strike price, then P1 is, the call option is worthless. I have K money, so that's the value of the portfolio I have. In the second portfolio, I will make this much money because it has gone down. And I have, this is the underlying stock I hold, so again the value is K. Yeah? So if I held these two portfolios, it turns out that after time T, at the time of maturity when I'm exercising, both have the same value. Okay? The no arbitrage argument says that if that is true, then right now also they should be the same. They should not have a price difference. Okay? So that extends to time T equals 0, so then this relation, these two, this plus this should be equal to this plus this. So what this tells you is that if you define a call option and a put option, matures at time T, then irrespective of anything else, this relationship holds. So the money you pay, the value of the call option and the value of the put option are related by this. Okay? So what that would mean is if I derive a formula that by solving differential equations to derive the value of the call option, I won't go through the same exercise to derive the put option, I'll just use this parity formula to catch up. Okay? Yeah.
Sorry, I don't think I quite understand call and put options.
Okay, yep, okay, go back. Okay, so I'm going to say, it's not particularly nice. Okay, so here is time. Okay, and I have an asset S, whose value is fluctuating. Okay. I'm sitting here at time naught, and the value of this is S naught. There is some time in the future, T, which is 6 months from now. So I'm going to now take bets. I'm going to tell you that if in 6 months' time, the value of this stock, so I'm going to give you a contract, word it this way, which gives you the right to buy this stock at price K, okay, at time T. So you will have a piece of paper in which I have signed, yeah, which gives you the right to buy Southampton shares at price K at time T. Those are the two things that are there, and my signature.
So that's not given as the price is anything. That's just that is your.
Yeah. So this is the right you have.
So even if it's gone below that, they still. So they don't actually have to buy that. They just have the option.
No.
They
Yeah.
have the
Correct.
option.
It's just an option, right?
Okay.
So now you have this contract.
Yeah.
Time T arrives. You look at this contract and look at the screen. Yeah. If you find that the stock price is here, then you know that you're going to make money.
Yeah.
You will come to me with this contract and say, give me. Yeah? Suppose the stock price is kind of here,
Yeah.
you're clever enough not to do this. Yeah, that's the argument. So that's the payoff function here.
Okay.
Yeah? So until the stock price hits K, you don't get any money for owning this contract. Yeah?
So what do you gain from writing that contract in the first place?
Right, so there are hedging arguments. So suppose I want to limit my risk as a result of these things going up and down. Yeah, so I would write a contract. So put is easier to explain. So if I hold a certain value of stocks and a certain value of put options I have bought, if the value of my stocks have fallen below a certain threshold, yeah, then I would go and exercise the put option and limit the risk that I had. You see that?
I'm not sure I follow.
Sure. Okay. So suppose I have a stock. Yeah, I bought one share of Southampton.
Yeah.
Yeah. Now this one share of Southampton might go down, might go up. So if it goes down below, if it goes down a lot, and I'm going to lose all my money. Suppose I spend a little bit of money and make a deal with the bank. I'm going to buy from your put option. I will have the right to make some money when Southampton stocks fall below their strike price.
I think I asked the wrong question. I was asking, what does the person that writes the call option gain from writing it? But you just said they can sell it, so I understand that.
Right. So yeah. So it's these are like gambling to some extent, right? So you have all these instruments sitting there. You can have mixtures of these instruments to manage your risk, manage your exposure. Yeah. Yeah.
I mean, the question is, if I want to buy one of those,
Yeah.
who will I buy it from?
Oh, the exchange, the stock exchange.
And
yes.
what do they gain?
What is the exchange gain? The amount of initial money you're going to pay to buy
So
this.
I'm paying to have this option.
Yes. Yeah.
Okay.
Yeah.
How can people get profit buying put options?
So it's not.
They think.
I know, yeah. So at the end of the day, this is uncertain, right? So there's uncertainty. Okay. So you don't know what the strike price is going to be. Okay. So if you have bought a put option on Southampton, yeah, with the knowledge that the Vice Chancellor is going to resign, yeah, then you're going to make money. So people are guessing. Why do people bet on horses, right? Yeah. But there is the positive element to this is that you have invested in some stocks, or you are trying to do a future transaction across currency boundaries. The availability of these instruments can be used to limit the risk that you take. That's the key. Yeah. So if you are going to, if you're doing a lot of foreign exchange transactions where your money is going to come from Greece in 6 months' time, say, yeah, and you're a little bit nervous about this, yeah, then what you do, you spend a little some other money and buy some options contracts and try to protect yourself. And the guy who sold you the options contract is betting that this disaster won't happen. Yeah? So if the disaster doesn't happen, this guy makes money because the money you paid. You're scared the disaster might happen, yeah, so you want to protect yourself. If the disaster happens, then you're not collapsing completely. It's managing, limiting risk. And you want to manage and limit your risk. Some guy out there thinks that you are over scared, so he's going to sell you something and make money. Yeah, does that generally make sense? And you can play a lot with this, and so you can have a combination of these. Yeah. So if you have a combination of these, you can have curves like, what's that? So below some other threshold I will make money, over some I won't make money. So something at K1, something at K2. Yeah? So buying a combinations of these, you can limit exposure that goes outside some range. You might think if the stock price stays within this range, I don't really care, I can manage that. If it goes outside, then I want to protect myself, I want to limit the loss, so I might go and buy some contracts. Okay? Okay, so what sort of thing we will do with this? I'm going to go very, very fast through a lot of algebra, but we're not going to take that algebra in now. I'll try and tell you what the kind of assumptions, steps, the kind of things we're going to deal with. We will write models of dynamics, how these stock prices might change. So remember I wrote this model? Yeah, this graph. What's a convenient algebraic way of describing that? And can I manipulate that to derive something? Okay? The Brownian motion, geometric Brownian motion, is a typical model that we use here. And that says the change in the asset price, there is a drift term here that says it's proportional to what it is now, and there is a noise term. So this asset price value is multiplied by noise term. Okay? And this noise term drives what's known as a Brownian motion. The idea comes from physics, things that are particles that are moving randomly. Yeah? So you would write to say that the change in something is some random number times square root of a small increment in time. And this random number is between this not 0 and 1, is normal distribution, 0 means 7. Yeah? And a very specific reason for taking it like that is that the variance of this, as you observe a particle jumping around according to Brownian motion, the variance scales uniformly, linearly with time. Yeah? So you'd like to think of that kind of a convenient model and plug it in. We then have this idea that I flashed this at you earlier. This is a stochastic differential equation. It's very nasty because the increment term has randomness in it. Yeah? If you write normal differential equations that you are familiar with, you would write things like dx by dt is some function of t. Yeah? When you write that, the increment, that's dx, is a deterministic function, therefore you can solve that differential equation easily. Okay. With stochastic differential equations, what happens is the increment term has noise in it. So if you go from, take a small step, then where you will be is random. Okay? And you take another step, it will be random, right? So you can't talk about a path, a single path that a solution will take. There's a probability of different paths that a solution will take, and that probability is governed by that kind of stochastic thing that sits there. Okay? So that's a tricky business. The way to handle that tricky business, in this particular problem, there is a thing called Ito's lemma, and this Mr. Ito has said that if you have a variable that follows this motion, then a function of that variable, yeah, its evolution will follow a particular structure. Okay? So we have S is our variable. S has a particular, obeys this geometric Brownian motion. If this is true, then a function of this variable will have a particular structure. And that particular structure is quite long, and that particular structure will look like that. Okay? What has it got? The change in that function over a small step, yeah, is related to the change in time and that stochastic term by this relationship. And the little things that come here are not too horrendous, even though this equation is that long. The little things that come here is the derivative of that function with respect to time. Yeah? Derivative of that function with respect to the underlying variable s. Yeah? The second derivative, the reason this second derivative comes in is diffusion. So anything, whenever you see this term, this has to do with diffusion. So you start, I don't know, you smoke here, and the way the thing diffuses in the medium relates to two things. One is how does concentration change with respect to time? The other is how does it change in space? Yeah? If it's a diffusive process, the second derivative with respect to that underlying variable is important. Okay? So even though this looks very long, it consists of a number of terms that we can identify if we knew f as a function of s and t. Yeah, that's the catch. Okay? So that much weighting a small step in time, plus the variance that we saw, sigma is the weighting term on that on the stochastic part, the derivative of the function with respect to the variable times a small noisy increment. Okay? So that comes straight from Ito's lemma. And what we can do is, if we look at that Brownian motion, geometric Brownian motion, and look at what would happen to the log of that variable. So S follows that motion, sorry, that dynamics. We can ask the question, what happens to log of S? Yeah, so log of S is a function of S. Yeah, so what I said here is going to apply. Yeah, and this one has that term, that term, that term. Our F is log of S, so I can calculate all that. I can calculate the derivative with respect to time, 0. I can calculate the derivative with respect to S, 1 over S. Yeah? Second derivative, minus 1 over S squared. All I'm doing here is differentiating log of S. Yeah? Why am I doing this? Because I know from stochastic calculus, I've looked through the book very carefully, that tells you that if you have that motion, which seems kind of sensible when compared to the picture that I wrote here. The picture I drew here says there is some drift term, so little by little is going up, and there's a stochastic term. Yeah? So if I write it down like that, then I can understand this one, I can plug in those expressions, and I get a term like an expression like this. Simplifies. Okay? What that tells me is that because this is drawn from a Gaussian random variable, the log of that asset price will have a normal distribution whose mean is this one, and the variance is that one. Okay? So a simple Brownian motion model that physicists have been doing all the time, when I think my stock prices might be doing this, tells me that these asset prices are going to be log normal. Log of the asset price is going to be normal distributed, and I happen to know what the mean and variance are. And this is something I can use. Okay? Is that kind of clear? Yeah, this is what I'm doing. The only thing to note here is that, okay, the mean will depend on the starting point plus some offset, which is proportional to time. So as time goes up, the mean is going to go up like that. Yeah? The variance, as time goes, will scale linearly. Yeah? So if we assume this is the model, then with time, the variance is going to go up and up and up. Yeah? Okay. So what we will do from this one is we will skip. So this is what we just saw. Yeah. We will derive what's known as Black-Scholes model. We'll do this on Monday. And what Black-Scholes model tells us is that if you had that assumption, then the price of a call option from this can be derived by assuming this time series and constructing a portfolio which is trying to be risk neutral, that there's no arbitrage in that. By coupling those two and going through all this we will go through on Monday, we hit a set of equations like this. Okay, this is it's a lot of algebra, but it is not outside the scope of your thinking, imagination, algebra manipulating ability. Okay, this I bet. Okay, what has this got? We'll hit a formula. A formula tells me the price of a call option is what is the current value of this one, yeah, times a function. I think this should not be equal, it should be times. I'll check this out. The kind of terms in this are there's a log, there's the R, the sigma, 2, the time, and so on. Yeah? And this n is just the cumulative normal density. Yeah? The integral of the Gaussian density. That you know, e to the power minus y squared by 2, integrated from minus infinity to some number is the cumulative norm up to that point. Yeah? So So cumulative norm we can look up somewhere. We can plug this in, we can calculate this D1, D2, plug this in, I can get a price for a call option. But I can only do this under conditions of this particular assumption that the stock price follows this. And the consequence of that through Ito's lemma is that the log of that asset price is normally distributed, and I know what the mean and the variance of this are. Yeah? And we'll see on Monday how I can construct a portfolio that will achieve that. Okay? And like I said earlier, if I knew how to price a call option, I will use the put-call parity to price the put option as well. Okay? And this Black-Scholes model is very, very widely used. It's one of the most popular ways of pricing options. And we will see this works when you make this particular assumption about what the dynamics of the stock prices are. When that stock price is not dividend yielding, that is between now and T, that stock is not paying its shareholders a dividend because we have made some profit. Okay? It is also true only for European style exercise. The exercise is not allowed in between. Okay? So under all those restrictive assumptions, I can get a closed form formula, which at first sight might scare computer science people, but there is no single component that's outside the scope of your ability. Okay? Is that kind of an accurate statement? No? You will not know this. Okay, so you will know this soon. We'll do some experiments on this. Okay, so what we will then do, yeah, so I'm going to stop in a minute, but what we'll then do is ask, can I have a numerical version of doing exactly the same thing? To do that, I will build a binomial model, and I will say, okay, so the stock price was this at this point in time, and then I will shock it. It will go up and become some u times s naught, and it will go down, becomes d times s naught. Yeah? And the underlying, and the price of the options, the value of the option was f naught, it goes to fu. If it goes up, it goes ft here. Okay? We will ask the question, what should these shocks be, the u and the d be, to match that continuous equation that I wrote? Okay? The equation that I wrote was a continuous equation of a geometric Brownian motion. Yeah? I'm going to model this one by walking on a tree like this. So I've drawn just one piece of this. I'm going to jump. I'm jump here. So I can construct a tree like this to represent precisely what I have drawn here. So this one I drew by assuming there is a continuous process whose increment is going linearly plus a random jitter. Yeah? That's a continuous process. I can think of this in the discrete world, which is nice for computer scientists like me, where I say, oh, I started here, I might have gone up here, I might have gone down here, and then from here I can go up or down. Yeah? And I have constructed this to make life easy because this down is the same as that up. So I made a simpler tree, a lattice than otherwise. Yeah? And then I would ask the question, what should parameters of this be in order to precisely match this one? Okay? You can imagine if I split time to fine slots, yeah, then asymptotically I will prove to you that this one can model that one. Okay? So if in the continuous world, if I assume this continuous function, I can derive a closed form formula for the call option. I can do exactly the same thing on a tree like this, on a lattice like this, and when I do to very, very fine time scale, by sending the time scale to 0, I will have the same result as that one. Okay? And then I can do more advanced things. Then I can do on this tree, on this lattice, things like American style exercise, which I can't do in closed form. Okay, so that's the elegant structure that we will have. How would I do this? So we're going to stop now. We'll go through some of these, some of these, some of these. This is what we're going to see on Monday, okay? So don't get too scared. It's dead simple, I can tell you. We'll do this sort of thing. So numerically we will do, so start from 150, goes up, price can go up or down, go up or down, go up or down, go up or down, up or down, yeah. And then if I thought the stock starting at 50 can have these possible values after 5 steps, yeah, and I have an option contract whose strike price is 50, then I know in these cells it's worthless. In those cells I will make profit. Yeah, I'll cash it and make profit. So what I can do at this juncture is actually value what the option contract option is worth. It's worth this much, this much, this much here, and 0 here. Yeah, and then I can work back. What might it have been before, and back, and derive the correct value for the option. Okay, so that's that lattice structure will be an approximation to the formal way of doing it under precisely the same assumptions. Okay, and we can calibrate. Okay, I'm going to stop now. I'm so pleased I did this picture.
然后他说 lattice structure，
So,
包菜
Tom and Mary.
对，我是想说。